This is an overview of Tuva EMPI. So the problem that we're trying to solve is the problem of patient matching. What that means is that you could have different records across different data sets that seem to represent different people, but they might correspond to the same person in the real world. For example, here you could have slightly different spellings of a name, you can have different source IDs, a date of birth could have a typo. We need to be able to say, if these records represent the same person, they should get the same person ID, and we should assign them all to the same concept of a person in our data set. In order to solve this problem at scale, there are three core pieces that are key to the solution of this. So I'm going to walk through these three pieces in more detail. First of all, we need to do record matching. So this means identifying different records in different data sets as referring to the same person. So for example, here are two records. We need to be able to compare them using the demographic features available for those two records and determine whether or not they correspond to the same person. So really all we need is an algorithm that takes two records as input and spits out the probability that they represent the same person. So this is just a pairwise comparison of records. And this can be done in different ways. You can do it with probabilistic techniques or deterministic rules. If you use deterministic rules, you can predefine rules that define whether or not two records are the same person. There is an open source Python package called Splink that is maintained by the Ministry of Justice in the UK that has such an algorithm for probabilistic matching. It uses something called the Filegi-Sunter model, which is a statistical model for record linkage. And the way this works is that it uses probabilistic techniques and it takes as input different demographic features available for each record, and then based on those values, it compares two records and determines a probability that those two records are the same person. Different demographic features used as input can get different weights in this comparison depending on the statistical distribution of your data set. So for example, if you have a data set where every record has the same value for city, because for example, you're only getting claims from a single city, then that field doesn't get a lot of weight in determining whether two records are the same because it doesn't distinguish between two different people. But if another field has a high cardinality and has many different values across all your records, that field might be weighted more heavily. The important thing to keep in mind is that this only gives us the probability that any given pair of records represents the same person, but it's only doing pairwise comparison. The next thing we need is an algorithm that groups records into people. So we need a way to recursively traverse all the probabilities linking different records to group records into people. If you only have a table that lists every possible pair of records and the probability that they're the same person, that's not very useful. What you actually need is to be able to say, record A is 90% likely to be the same person as record B, and record B is 95% likely to be the same person as record C, and then record C is 97% likely to be the same person as record D. You need to traverse this chain of linkage algorithmically and say all of these records correspond to the same person. So mathematically, this is just exactly the same as the problem of defining an equivalence relation on a set and then using that equivalence relation to partition the set into equivalence classes, where each equivalence class is a collection of records and is identified as a single person in the real world. Now, the third component that we need is a user interface where people can review and approve matches. We've built a user interface where you can use in a human in the loop workflow for somebody to log in, see the matches that have happened, review them, approve them, change them, and then integrate this with the rest of your workflow in your data warehouse. So the Tuva EMPI solution has all three of these components. It has record matching, doing pairwise comparison of records, and it's using the Splink algorithm in the backend to do this matching. Then we've built a person creation algorithm that recursively traverses chains of linkage to create partitions in your data and assign a unique person to each of these partitions. And then we created a UI where people can review and approve matches and integrate that with the rest of their data workflow. So all of these three components are directly integrated into the Tuva data model. And if you have your data in a cloud data warehouse sitting in the Tuva data model, there is a pipeline that integrates your data model to the Tuva EMPI solution. It runs in a containerized application where all three components for matching happen. This creates a universal person ID that then gets integrated back into the data warehouse, and all your data marts automatically run on this universal person ID that is created. So it's a seamless integration with your data flow, unlike other EMPI solutions that are very difficult to integrate with your data flow because you have to figure out what are the pipelines to integrate to any data mart, to your different data sources and so forth. This just runs out of the box if your data is in Tuva.